I'm going to talk about ideal and non-ideal solution in this video. Ideal solutions are the ones which obey Raoult's law. So the solutions which have total vapor pressure Pt is equal to XA naught plus XB Pb naught are the ones which are ideal solutions, and non-ideal solutions are the ones which do not obey Raoult's law. So for them, total vapor pressure Pt is going to be not equal to XA naught plus XB Pb naught. Now there are two cases. One is positive deviation and the other one is called negative deviation. So if total vapor pressure above the solution is greater than what was predicted by Raoult's law, so XA naught plus XB Pb naught, those solutions are called to have positive deviation. And similarly, if Pt, that is total vapor pressure above the solution, is less than XA naught plus XB Pb naught, they are called negative deviated solutions. Now let us try to examine what is the cause of this deviation and how we can determine which solutions will follow which deviation. So it all depends on the intermolecular force of attraction. In case of ideal solution, the force of attraction between AA molecules and BB molecules are similar to the force of attraction in case of AB molecules. So we have taken liquid A and liquid B and mixed them together. So we are talking about intermolecular force of attraction between A and A, similar type of molecules that is, and similarly intermolecular force of attraction between molecules of liquid B, and AB is intermolecular force of attraction between molecules of A and B when they are mixed together. So in case of ideal solution, we are saying the force of attraction in all three of them are of similar nature. In case of positive deviation, the intermolecular force of attraction between molecules of AA and BB are greater than intermolecular force of attraction between A and B type of molecules. Now let's try to understand this in a little more detail. So what happens is, if the force of attraction between AA and BB are more than force of attraction between A and B type of molecules, so we are saying that molecules in the mixture, that is AB, are comparatively loosely bound, so they can very easily go into vapor state. So effectively there will be more number of molecules in vapor state than in case of ideal solution. So basically vapor pressure will be more, and that is why the Pt is greater than what you calculate from the Raoult's law. Similarly, in case of negative deviation, the force of attraction between AB molecules is more than intermolecular force of attraction between AA and BB. So we are saying molecules are more tightly bound, so it becomes difficult for them to go into vapor state, and hence the pressure exerted by them is comparatively less. The third difference between these three solutions is that in case of ideal solution, there is no heat evolved or absorbed, and similarly there is no change in the volume. That is, if you mix 1 liter of A and 1 liter of B, you will obtain 2 liters of solution. Whereas in case of positive deviation, we are saying that delta H of the mixture is greater than 0. So that means to prepare this kind of solutions, you will have to supply some amount of heat, and also delta V mixture is greater than 0. So what it means is, if you mix 1 liter of A and 1 liter of B, the volume of the solution that you will obtain will be greater than 2 liters. Now why that happens is, as we said that intermolecular force of attraction between AB molecules is less, so we are saying that molecules are loosely bound, or distance between molecules of A and B will be more in liquid phase. So effectively the space occupied by these molecules will be more, and that is why delta V mixture is greater than 0. In case of negative deviation, delta H mixture is less than 0, so that is the reaction is going to be exothermic in nature. Again, the reason is because the intermolecular force of attraction is more, the bond formation is preferred. So basically you are saying that the amount of energy involved in this case is going to be less than 0, or some amount of heat is basically going to evolve. And similarly, because the intermolecular forces are greater, the intermolecular distances will be smaller, and delta V mixture will be less than 0. So if you mix 1 liter of A and 1 liter of B, you will obtain less than 2 liter of solution. Delta S mixture and delta G mixture is same in all the three cases. So delta S mixture is going to be greater than 0 in all three cases, and delta G mixture is going to be less than 0 in all three cases. So this is nothing but, you can say, the feasibility of the reaction is the same in all three cases. Now there are certain examples that you will have to look at. So the ideal solutions are formed when you mix benzene and toluene together, N-hexane, N-heptane, ethyl bromide, ethyl iodide, chlorobenzene, bromobenzene, etc., etc. So if you observe the kind of force of attraction that you will have in case of molecules of benzene and toluene are going to be same when you mix them together also. So that is why the kind of solution that they are forming are ideal solution. In case of positive deviation, you are looking at water and alcohol, primary example if I may. The force of attraction between water molecules is high because of the hydrogen bonding. Similarly, alcohol also will have some amount of hydrogen bonding within themselves. So the force of attraction AA and BB is going to be huge because of the intermolecular hydrogen bonding. But when you mix them together, they still form some sort of hydrogen bonding, but the force of attraction is not that much, and that is why it shows positive deviation. And similarly, there are certain other examples that you can basically go through. In case of, let's say, water and HCl, the force of attraction between H2O molecules and HCl molecules when you mix them together is more than intermolecular forces between H2O and HCl separately. So that is why it shows negative deviation. There are certain other examples that you can go through. Now let's try to depict the positive and negative deviation onto the graph. So if you remember, we had drawn this kind of a graph for ideal solution. So these black lines that I have drawn over here are nothing but the ideal case that we had drawn earlier. So this particular black line was representing PT, this particular black line was representing PB, and this particular line was representing PA. That is in case of ideal solution. Now when there is a positive deviation, what we are saying is both PA and PP will be more than the expected value, and so will be the value of PT. So total vapor pressure in this case will be more than what was expected according to Raoult's law. And similarly, in case of negative deviation, the actual vapor pressure will be less than what was expected according to Raoult's law. So again, in this case, the black line represents the ideal case and the red one represents the negative deviation case. Now I'm going to talk about something called azeotrope. So normally what happens is when you mix two liquids together, A and B, you expect the more volatile liquid to be present in greater proportion in the vapors. But as we had seen that PA is equal to XA PA naught. So there are two factors, XA and PA naught, on which partial pressure of A in the vapor phase depends. Now there might be a combination of XA and PA naught such that the composition in liquid phase as well as in the vapor phase becomes equal. So you cannot actually distill this kind of mixture, and this kind of solution is called azeotrope. So azeotrope is nothing but liquid mixtures which distill over without changing in composition, and they are also called constant boiling mixture or azeotropes or azeotropic mixtures. Now there are two types of azeotropes. One is called minimum boiling azeotropes. So when a non-ideal solution has a positive deviation, it forms minimum boiling azeotrope, and they boil at a temperature lower than the components A and B. let me explain you through the graph or diagram. Now let's make a graph of pressure versus composition of A in the liquid phase. Now the bubble point curve that is I have drawn in the black line is the one which has huge positive deviation from the Raoult's law. So according to Raoult's law, this particular line should have been a straight line joining these 2 points, but because of the positive deviation, this graph becomes like this according to positive deviation. Now the dew point curve looks, let's say, something like this, the red line. So as we had seen earlier in the phase diagram, this particular part of the graph represents liquid, this particular part represents vapor below the dew point curve, and the area between the two graphs is nothing but where coexisting phase liquid and vapor exist. Now this particular point wherein the two graphs are basically coinciding is nothing but your azeotrope. So why is it so? Because at this particular combination of XA, let's say you have a particular point wherein, let's say XA is 0.7, just for an example. So at this particular point, both XA and YA are going to be same. The red line represents the graph PT versus YA. What we are basically saying is, if you have this particular combination, liquid and vapor phase both will have the same composition, and that is why you cannot separate them out, and that is why it is called azeotrope. And if you look at the value of pressure of this particular point, it is more than both PA0 and PP0. So vapor pressure is more, so the boiling point will be less. We can also look at the same diagram in terms of temperature. So now if you look at the graph of temperature versus composition, that is again XA and YA. So the black line represents again the bubble point curve. The black line again will represent the bubble point curve, and the red line represents the dew point curve. Now again in this case, the point where both the graphs coincide is nothing but your azeotropic point. If you look at this particular point, the boiling point is less than both TA0 and TB0, that is boiling point of pure liquid A and B respectively. The part below the bubble point curve is nothing but your liquid, and part above the dew point curve is nothing but your vapor, and the part in between the two graphs is your liquid plus vapor phase. Now similarly you can consider maximum boiling azeotropes. So the solutions which show large negative deviation will form this kind of azeotropic solutions. This will boil at temperature higher than both pure A and pure B. So if you look at the graph of pressure versus again XA or YA. Now in this case, the point where the intersection of bubble point and dew point curve happens is below both PA0 and PP0. So vapor pressure of this particular combination is less than both PA0 and PP0. So the boiling point in this graph will be more than both TA0 and TB0. So this kind of solution is called maximum boiling azeotrope. Again, you cannot separate this kind of mixtures using simple distillation, because both liquid and vapor phase will have same composition. So basically the entire concept of distillation cannot be used to separate this kind of mixtures.